Thank you. I'll try to start every lecture by a recap of what happened in the previous lecture, just to start up your brain a little bit and get you on board again. Before even doing that, Elena told me there's been a question about the exercises last time, whereby you had to convert transfer functions into state space forms, and you had sometimes on your right hand side terms that may involve time derivatives of your inputs, and some have tried to handle that by basically naming these inputs as different things and treating them as different inputs in the system. Well, that's a clever trick, but it does not work. The problem is, if you want an intuition for why you don't actually have 3 inputs but only 1, is because these things here are actually not independent, if you think about it. If I give you u at time 0 and u1 at time 0, and then I give you the complete profile of u dot dot, this guy or these guys will define entirely the input and its time derivatives. i.e. you cannot say I'm gonna do whatever I want with my u dots and whatever I want with my u dot dot, because the time derivative of this one must match that one, all right? So you don't actually have 3 inputs, you have only 1, but it appears time differentiated in the function. So if you had 1 input in the beginning, even if it appears time differentiated, in your state space form, you should not have more than this input you have here, okay? Any question on that? Yeah?
How come can we can do that with, we can still do that with x, for example, our state, but shouldn't the state also be, for example, if we have one variable as x dot and one as x, shouldn't those be dependent as well? How come we can have those as separate variables?
Yeah, that's a very good question. Because indeed, when you have an x variable, for example, that's what you mean, right? That may appear also time differentiated. How come you can actually introduce different variables for all these guys? Right, that's what you're asking. Yeah, that's spot on. You do that, but you also reconcile this in your equations. So if you remember in the examples we had, that maybe was an acceleration and a velocity and a position. We were renaming this guy v, for example, for a velocity. But then we're also introducing an equation saying that v must match x dot, right? So let me refine my statement on this side if you want. You could, in principle, introduce all these variables, u0, u1, u2, as long as you would also add equations that ensure these things match correctly, right? So then you would need a bunch of equations saying that u1 must match u0 dot and u2 must match u1 dot. You could do that then, yeah. Then you would just shuffle more variables in your state space form. Okay? Anything else? All right. Okay, recap. Just briefly what we've done last time. We discussed state space forms. That's really going to be the bread and butter of what we will use in this course. So we will always look at models in this form or variations of that, and we'll get to that very quickly. And what you want to do is, once you write the equations underlying the physics of your system, you may have high order derivatives appearing. What you want to do is manipulate your physical equations until you get in a form that looks like this. And by this I mean only first order derivatives in your equation. And why do we do that? Well, we like to have kind of a single form. Now, if we can write our equations in this form, we basically describe entirely our dynamics via the function f and our output equation via h. So we are talking about two functions, and we should discuss the properties of these functions, and we can forget ODEs in some sense. One thing we'll get to quite quickly, I don't want you to be obsessed by this form. I want you to really think about first order derivatives here. And we'll see fairly soon examples where trying desperately to write your equations in this form is actually counterproductive, because you can do that, but you will get very, very awfully complex expressions in your functions, whereas you could write them in a much more simple form. And by that I mean, for example, you may want to keep your equations in an implicit form. So you don't try to extract x dot from your equations, but you keep them inside the function if you want. And under some fairly simple conditions, this is defining trajectories very clearly. So we'll get to that quite soon. Any question on that? One thing I insisted a bit on last time, that is, if your functions f and g are linear and time invariant, then you can write an explicit solution for your equations. You can write x of t is equal some functions you can write on paper. For anything else, you may have to rely on simulations. And we've seen exceptions last time with these examples of ODEs generating strange solutions like exploding or non-unique. There were like very special cases of nonlinear differential equations that you could solve without simulations, but most often you need the computer to treat your equations if they are nonlinear. And we've seen the linearizations of this kind of models, and if you remember what you need to do, first pick a point that is a stationary point of your dynamics. So essentially a point where the state is not moving anymore. You want x dot is equal to 0 at this point. And then you can actually write down a linear time invariant system that approximates your nonlinear dynamics at this specific point. So this will be an approximation of your system 1 around that point here. And by these delta variables, delta x, delta u, delta y, we are really talking about how far we are around our point x0, u0. Maybe just as an extension to this, it is possible to linearize a nonlinear system around a point that is not a steady state, but you need to do it very carefully. So we do that in some advanced questions on control. But for us, we will stick to this point of view. I just wanted to show you an example of linearization, actually. So we treated one on the blackboard last time. If you remember, we tried the linearization of this pendulum system. Just a mass hanging on the ceiling and oscillating around a pivot. So you have an angle theta that oscillates. And the equation in the state space form for that system were looking like this. So you should have that in your notes. We discussed that last time, and because of the sine theta, we have a nonlinear system, and you can linearize this system around different points. And we had discussed that, of course, you have two stationary points for the pendulum, one downward and one upward. This one is stable, he will stay around this point. This one is unstable. So, just want to show you this example. All right, so when you have to linearize a system, well, we may ask you to do that in the exam, and then you don't really have a choice. But if you do this in exercises, in your work, please do it on the computer. I have a small MATLAB code here that does precisely that for the pendulum. I'll post the examples I give you in the class, I'll put them on ping pong. And I advise you to cheat a bit on them and have a look at how the codes are working, so that you can quickly develop also your own ways of coding things in MATLAB. So this is a pendulum, and I will simulate both the nonlinear system and the linear system for different points and superimpose the trajectories. So this would be a simulation. I'm starting from theta 5 degrees, and the pendulum has no velocity. I'm checking here that I do have a steady state. So here I'm linearizing or looking at x0, u0 being the pendulum down. So it's oscillating around this 5 degrees, and that's the nonlinear model with the sine. If I superimpose the linearized model, that's the red trajectory, and we hardly see a difference here. So my linearized model is approximating the nonlinear dynamics very well. You can see a slight difference after 20 seconds, but nothing to worry about. So for example, if you consider the oscillation of the pendulum around this point with small angles, then it doesn't make sense to bother with the nonlinear system. You should look at the linearized one. That was for just a few degrees of around the stable point downward. If, say, now we go a bit beyond that, so let's say 60 degrees here. That's my nonlinear simulation. And the linearized one is now a bit different. Actually, you see that the general trend is the same. We have the same oscillation, but the linear system is oscillating a little bit faster, if you want. And after 20 seconds, the prediction you get from the linearized system does not really match the nonlinear one. So depending on what you want to do, looking at the nonlinear dynamics may make sense. Now this was simulations around the stable point downward, right? And let's try the other point now, just to see what happens. So now I'm gonna linearize the pendulum around the unstable point upward and simulate it both for the nonlinear and linear system at that point. All right, so now I have a different picture. And what you see here is really the pendulum going all the way down and up again, and all the way down and up again, right? That's what you see as a simulation, with theta starting at 180 degrees. Now if I superimpose the linearized simulation to that, I get something very different. Can you guess why is it so different now? I used 1 degree of delta x0 if you want, and I get a completely different trajectory.
Initial conditions?
Yeah. Should I help you? This point upward is unstable, right? Obviously the pendulum falls if I start it around this point. It's not gonna stay there. And that means whatever I do with this pendulum, unless I keep it up there, whatever I do with this pendulum, the theta is bound to become pretty large, or if you want, the delta theta is bound to become pretty large, just because the system is unstable. I may start with 1 degree, but very quickly I have 90 degrees and then 180 and so on. So my delta x0, if you want, in this case, will become large very quickly. And that means my linearized model will become wrong very quickly, right? So my linearized model may be correct around this, but very soon my theta is actually shooting from 180 to 500. And there my linearization is completely wrong. So my trajectory becomes completely wrong, okay? So keep that in mind when you play with linearized models, because these things actually matter. Question on that?
Can we linearize on another point?
Yeah. And I'll start having a different problem. For example, if I linearize at 90 degrees, what will happen, unless I pick my u properly, is that I don't have a stationary point. So I would need to adjust my u0 in order to be at the right, at the steady state. But I can still do the linearization. And here the linearized model is actually pretty wrong, probably because I'm not at steady state. I would have to check what happens there. If I introduce the right u0, then I should be fine. Okay. All right. Okay, quickly, last time I showed you 2 theorems that are not bad to keep in mind when you play with simulations. And the question we're asking there was really, if I write down an ODE in that form, I even dismiss the inputs, that's not the point here, will I have a solution, and will that solution be unique? And I gave you 2 fairly simple theorems actually that were treating this question. So at this one, if you can bound your function f via this construction here, we call this L the Lipschitz constant, by the way, but that's a detail. So for all x, y, regardless of which one you choose, you should be able to write down this bound. And you pick one L, and that must work for all x and y. So surprisingly simple functions like x squared would fail this kind of bounding. But if you can do that, then you can be sure that the solution exists for all time. The second theorem was a bit milder in some sense. All you need is that your f is continuously differentiable, which means you can compute the Jacobian of f, and that Jacobian itself is continuous. If you can do that, then the solution exists at least on some time intervals, and it's going to be unique. And you remember I had an example here where f looked like this, and that was failing this condition, and as a result, in this case, I had a non-unique solution to the ODE. So what I'm trying to say here, don't run around trying to test these conditions on whichever model you write down before simulating it. People usually don't do that. But if you simulate some models and you run into serious troubles doing that, just keep in mind that there are some conditions for a model to have a well-defined solution, and you may want to think about that if something goes wrong. Any question on that? Okay. So last time we started discussing about stability. If you have an LTI system in this form, so you have these four matrices A, B, C, D. All you have to do to assess the stability of that system is evaluate the eigenvalues of your square matrix A. And these guys will be complex numbers, typically. And if you find some of them with positive real parts, then your system will be unstable. Those with negative real parts will be fine. So as soon as you find even one eigenvalue with a positive real part, then you have an unstable system.